Hello, and thank you for joining me for this presentation. My name's Thurston Williams. I'm the Managing Director at Renolith. I'm an engineer with 30 years of experience across asset management, project management, maintenance, design, various roles. Our topic today is Pavement Nanoengineering, which is rather broad, believe it or not. So specifically we'll focus on the Australian local government context and mostly around regional and remote councils, their needs. And we'll also hone in on the Renolith product. It's one I'm most familiar with, and we believe it's the vanguard in this space. And my opening observation, rather blunt, is that the road industry is rife with greenwashing and obsolete, ineffective and unaffordable construction practices. Now, resilience and sustainability are the buzzwords of the moment, which is fine, but for me, a road network that disintegrates in wet weather is neither. To frame the discussion, local government has significant challenges to manage a huge network of roads with increasing traffic and inadequate maintenance funding. The accelerated damage from wet weather events, additional traffic, particularly the freight task, and increasing expectations from the community make it a really big challenge. So we have a fragile, unaffordable, unsustainable road network in summary. So what Renolith brings to the equation is an opportunity to do things better. So it leverages low-cost construction practices, which we're talking cementitious stabilisation, and it enables resilient roads to be formed, so that's impermeable, crack resistant, heavy traffic capacity, no problem. It's all eco-friendly because we're upcycling the in-situ material, and it works whether we're talking sealed or unsealed roads. And it's a well-proven practice. Over 70 million square metres of pavements around the world over 30 years, not a pothole yet. So what we'll go through is I'll give you a quick summary of the Renolith product. We'll explore the particular needs of local government and some of the challenges that we have. And then we'll go into more detail on the Renolith product and nanotechnology in general. And we'll talk about the business case and the opportunities that arise. Quick summary of the Renolith product. In functional terms, it's just a method for creating nano-engineered materials, usually roads. In technical terms, it's a nanopolymer admixture for cementitious binders. So think cement or things like cement. The chemistry is complicated. We don't need to go into that. The reason we want to use it is we can eliminate the key damage modes that we would see and distress modes that we'd see of pavements. So ruts, cracks and potholes basically. And that allows us to radically reduce the triple bottom line costs of our pavements. So that's dollars, that's environment and that's social costs. Now the way it does it is by creating a high-performing cementitiously bound composite. Primarily it's about preventing shrinkage cracking and fatigue cracking. It also improves the material properties such as tensile strength and modulus and impermeability. Those things are good but not critical. It's really about the shrinkage cracking is the key to it all. It's needed now, it's available now, it's commercially proven over a long time and it's compatible with extant specifications and construction practices. So what it all comes down to is a much better triple bottom line, sustainability. So people, profit, planet in simple terms. We can keep costs down, we can recycle all the in-situ material and get a much better road from it. And that all means low carbon footprint and so on. And those roads will last for a long, long time. So now let's briefly explore the context to make sure we understand the problem we're trying to solve. So I've borrowed some slides here from the recent Grattan Institute report, Potholes and Pitfalls, How to Fix Local Roads. It's got some really good detail in there. Now, the Grattan view is it's all about funding. No argument with that. There's clearly some funding shortfalls, both in how it's administered and the amount of money that's being put into road maintenance. But I would argue that that's only part of the puzzle, and the bigger piece is let's choose construction practices that are more aligned to the needs of the community and of the assets that we're trying to maintain. So in this case, we're talking about stabilisation and nanotechnology. And These things are within the control of local government to adopt, and really you can design a road that won't pothole, and that's quite straightforward to do, and particularly now with some of the new funding models that are coming through, such as the Safer Local Roads Investment Program and Roads to Recovery. It's all quite doable on current budgets. The first challenge, as we mentioned, is about trying to manage vast road networks, particularly for regional and remote councils, and limited scope to raise revenue. So whatever we do needs to be low cost construction and maintenance solution. Challenge number 2 is that roads are carrying more traffic, and that trend is projected to continue. So more traffic means more fatigue damage, and the maintenance spend hasn't kept up with that. So we need a better fatigue life per dollar spent on construction and maintenance. Challenge number 3 is that there's a vast difference in the expected lifespans of roads, and some of that's geology and the traffic and the circumstances, but there's also clearly a difference in the way construction practices occur in some jurisdictions. What we need is a method that gives a long life and deals with the traffic and environmental issues that are particular to a given council. This is a recent report out of Austroads, talks about some of the challenges around bringing on zero emission heavy vehicles. So big battery packs add to the weight, and that introduces new challenges. So if everyone wants to go green, the additional weight from these vehicles is going to cause additional damage to the roads, and there's no easy solution to that, particularly when the network is, as they say, thin unbound granular pavements, mostly around the country, which don't perform well in wet weather. Looking at the Victorian situation, this recent survey from RACV, number one issue around the country, or around the state, is potholes and poor road condition, and that's showing up in the media as well. You can't open the Herald Sun without getting lambasted by the community upset around the state of roads. The NTRO do an annual survey of the structural condition of Victorian roads using their iPave technology, basically a truck with sophisticated sensors. And in 2021, the government spent hundreds of millions of dollars improving the road network, raising the proportion of good roads from 2% to 19%. Then it rained. By 2023, the roads were significantly worse in condition, and none were in good condition. None. So where did all that investment go? Clearly, lack of investment isn't the main problem. It's wasting money on rectification methods that aren't resilient. It makes a mockery of the whole idea of a circular economy. In New South Wales, we can see similar challenges, although not quite as severe, but an 80% increase in infrastructure backlog over the last few years. Natural disaster events are increasing in frequency and severity. There's a growing realisation that much of Australia's road network is very fragile and unable to cope with the climate reality we face. So in Queensland at least, they've started to get in front of this perpetual problem. There is a long way to go though. Let's say you are putting together a requirements specification for a road with multiple stakeholders, each with really ambitious requirements around cost, sustainability, resilience, pavement life and so on. You give this spec to your engineers, the spec below, and they'll tell you you're dreaming. So that's true using conventional approaches, though it's hard to achieve more than a few of those criteria. The good news is that with Renolith nanotechnology, it's actually quite straightforward to achieve all of these. So that's our segue into Renolith. We'll now go through the product, but we'll start with the introduction around pavements for those who aren't technical, and then we'll talk through the reasons for using the product and some case studies and how it all works. Starting with pavements and stabilisation. Pavements, it's really we're talking a road or things that are like a road, car parks, hard stands, paths and so on. We're going to talk just about flexible pavements, which is how most of the roads in Australia are done. You can use the product in rigid or concrete pavements, but we won't really talk about that much. So most of the pavements in Australia are unbound granular pavements with thin bituminous wearing course. Now the problem with this type of structure is, number one, is resilience. So ruts and potholes and water damage is really susceptible to these things. And the other that's increasingly becoming an issue is sustainability. So if you need to rehabilitate such a pavement, you have to dispose of the spoil, you have to use a lot of virgin quarry material, and that brings with it a lot of costs and energy use and carbon footprint attached to that. With flexible pavements, the main alternative to unbound material is to bind or stabilise the base layers, which improves the engineering properties. Now there's several ways to do that. The most versatile, and our focus today, is cementitious stabilisation. Unbound and lightly bound pavements are mostly reliant on friction to maintain structural integrity. We're particularly interested in the tensile strength achieved with bound materials. It acts more like a beam, and that has important benefits for how that pavement performs. To explain that, the diagram on the left shows how a typical pavement, an unbound or a lightly bound pavement, works. The pavement needs to transfer the load from the traffic, from the wheel, through the base layer down to the subgrade. And really it's only doing that through shear strength, so it has to be quite a deep pavement to do it. When you have a bound pavement, your pavement can be much thinner, and that means because it acts more like a beam, you can actually transfer those forces much more easily. When we talk cementitious stabilisation, another word for that is soil cement. You can think of it as a special type of concrete. In terms of process, we spread the binder, cement or something like cement. We mix the soil, the binder, water, and possibly an admixture together. We shape the pavement with a grader and then compact it. It's a very fast and low cost process, and it's used all around the country and all around the world. The Austroads guide sums up the business case well. Stabilisation technology provides a cost-effective method of improving the long-term performance of modern pavements. The main technical challenge is cracking, shrinkage cracking and fatigue cracking. The fatigue cracking from traffic is easy enough to deal with by increasing the amount of binder and or thickness of the bound layer. The shrinkage cracking is not so straightforward. As a rule, more binder means a more heavily bound material, which means better fatigue performance, but more binder increases the severity of shrinkage cracking. Prevention of shrinkage cracking is Renolith's superpower. So this picture shows a trial road built in northern Italy in about 2005. It had a base layer of stabilised material with a thin spray seal wearing course. The base for the right-hand lane used cement-only stabilisation. The base cracked and those cracks propagated up through the wearing course. For the left-hand lane, the base was constructed with cement and Renolith, and hopefully you can spot the difference. If the key technical problems we're trying to solve with cemented materials are cracking, shrinkage cracking and fatigue cracking, the way we do that with the Renolith product is by improving the material properties. We reduce the drying shrinkage. There's a self-healing aspect to it, which we'll talk about when we get to the nanotechnology section. We're increasing the strain limit of that material. We're increasing the elastic modulus and the flexural strength. So that means no shrinkage cracking and reduced damage from traffic. And that means we have lots of opportunity to optimise the design of that road. So we can use poor or marginal materials. We don't necessarily need a granular asphalt or granular overlay or asphalt overlay. Pavement can be thinner, and there's no upper limit on the strength of that pavement or the cement content. And that has a range of benefits. So we get a much higher performing pavement, we can keep the construction costs down, we have very low carbon footprint, we can get a very high recycled material content, and we don't need to maintain it. In the case of an unsealed road, we can just use that base layer bound as it is. A lot of the work that's happening in the nanotechnology space is focused on concretes, and certainly Renolith can be used in concrete, but the way most pavements in Australia are done are flexible, which means either unbound or cementitiously stabilised. So the sweet spot really for the product in the Australian context is in bound or heavily bound layers. So that means anywhere between, well, I say 2 to 10 megapascals of compressive strength, might be between 3 and 6% of cementitious binder. And that gives us the best of both worlds. We still have the ease and low cost construction of flexible pavements, but we do develop this chemical bonding and much improved tensile strength of the material, which gives the performance advantages that you don't get from lightly bound materials. But it only works if we can get that shrinkage cracking dilemma resolved. In stabilisation, the conventional approach to manage the cracking is to impose constraints on the design. Some soils aren't considered viable. Binder content is typically limited to reduce the severity of shrinkage cracking, which means limits on the performance of the material and how that material is used in a pavement. Moreover, you can never really be confident that the design is going to last because of the combined effects of drying, shrinkage, traffic and environmental effects. Engineers being conservative types, this often results in an over-engineered and expensive pavement. Renolith nanotech significantly improves the engineering properties of bound materials. Possibly its most important function is to prevent shrinkage cracking, and this enables much more flexibility in the design and results in better pavements. It also significantly reduces the risk of premature failure because unpredictable shrinkage cracking is removed from the equation. So we only need to design for fatigue. So that's cracking. Now let's talk about resilience. With recent floods, we've become acutely aware of the need for more resilient infrastructure. However, achieving this in an affordable way presents a technical challenge. For example, granular layers can disintegrate quickly in adverse conditions, whereas cemented materials tend to crack, providing vectors for moisture ingress and eventually potholes. It's not that we can't build resilient pavements. We certainly can, and there's several ways to do that. Perhaps foam bitumen, deep strength asphalt, concrete. They're all quite resilient methods, but they're unaffordable for the most part, particularly for regional and remote councils. The way we tend to do things mostly though is gravel unsealed or an unbound granular base with a spray seal, and sometimes cementitious stabilisation definitely improves the resilience. What Renolith does is it allows us to get the resilience that we would from these other methods such as foam bitumen, but we're still that much more cost-effective approach such as cementitious. This is just one study out of India where they assessed the effect of adding Renolith to a silty sand material with different levels of cement. And as you can see, we get about 100-fold reduction in the permeability compared to cement only. So it means you get that impermeable state much earlier. You don't need as much cement to do it. And similar findings in a study out of Russia. So this was testing NTS, which is the same product as Renolith, in swamps of Siberia. So pretty challenging conditions, as you can imagine, with the moisture and the freeze-thaw conditions. And yeah, they found a significant improvement in the properties of the material, and they were able to use it in all sorts of applications, permanently waterlogged underground applications. To summarise all of that, the solution in principle as put forward by Engineers Australia is to use more climate resilient and recycled materials in our roads, increase waterproofing and embed sustainability and resilience in principles in all stages of the asset life cycle. And in the Renolith equation, we are doing that. We are recycling the in situ material. We're not getting any cracking. We're not worried about water. So we have a climate resilient pavement and we don't have any potholes forming. Next, we'll look at the triple bottom line business case for a couple of scenarios. These are case studies that we've done in Australia before, and they're very much aligned to the Safer Local Roads Investment Program, which is fairly new in Australia, but it's certainly a move by the government to improve the resilience and sustainability of our pavements. First one was a trial done in Queensland by the Department of Transport and Main Roads, now TMR now. So they upgraded the in-situ pavement was an unsealed road having a lot of trouble with inundation and rutting, corrugations and failures. So they stabilised the in-situ material to 200 millimetres with Renolith admixture and cement, no wearing course. And you can see that 4 different types of soil they were dealing with, each had a different level of cement applied, and they all performed well. The one, probably the most important one there, is the 6% cement, because as you can see at that level of cement you would normally expect pretty severe shrinkage cracking, but it didn't happen. And the trial report concluded that the Renolith product, when mixed with cement and stabilised, is a most efficient and cost-effective product for the upgrading of soil pavement roads. So looking at that in a whole of life cost scenario, the orange dotted line is what it normally costs to maintain an unsealed road. So you have to do a resheet every now and then, and you have to grade it all the time, and those costs accumulate. If you do conventional cementitious stabilisation, that's the dotted blue line, you can reduce those costs because you delay the resheeting process and you don't need to grade as often. On the green line though, that's Renolith Nanoengineered. You do it once and you're done, and there's a higher upfront cost of course, but you don't have to keep maintaining it. There's no maintenance required. And all of the, I guess, usability advantages that come with having that all-weather pavement. The next case study we'll look at was the New England Highway trial back in 2002. So the department selected a 700 metre section of the highway to trial various, at the time, novel additives. So one section with lime, the next was with Renolith and cement, polyroad on the third, and the control was with no additive. At the time of construction, so the Renolith cement section performed best, highest CBR, lowest plasticity, highest compressive strength and lowest deflection. Fast forwarding 20 years, if we look back to the original trial report, the expectation was that the heavily bound sections, so that's the lime and the Renolith sections, would crack, and those cracks would reflect through to the wearing course. Certainly for the Renolith section, that hasn't happened, and that's 21 years later. So if it hasn't happened yet, it's not likely to, and that really does reinforce the idea that shrinking cracking is something that doesn't need to be such a concern in the design. Looking at the triple bottom line costs of a scenario like this, let's say the New England Highway rehabilitation project or something like it, there's a really good paper by White and Young that talks about the triple bottom line costs of various pavement solutions for local roads. Worth a look there. There's a link there in the bottom. The two most common that might be used is a dig out and replace strategy or a cementitiously stabilised, lightly bound pavement. So that's the first two columns there, and certainly the cement stabilised gives a better result, brings the thickness down, the costs down, the embodied carbon down, certainly a lot better than the conventional dig out and replace with unbound granular material. What the Renolith Nanoengineered option is one step better again. You can see we're quite a bit thinner than either of the other two pavements, which allows us to bring the cost down, brings down the carbon footprint, and ultimately it's going to give a much better result. It'll last longer from resilience, from traffic, and can handle heavier vehicles with little trouble. So now let's explore a bit about what nanotech actually is in this context. Historically, people have understood Renolith to be a polymer product, which it is to an extent, but that's really just the tip of the iceberg. Really, the hard work is done by the nanomaterials, and this is something that's really not been understood by the market or by the many copycat products that are out there. No one else is doing this approach to nanotech, and this is why Renolith is so much more successful than other products that are on the market. So we call Renolith an admixture, and really an admixture is just something you would add to cement or cementitious material. It's used all the time, of course, in concrete or mortar. There's various types, water reducers, plasticizers, set retarders, all sorts of different types that we use in concrete all the time. It tends not to be used so much in pavements because it's well, certainly flexible pavements, because it's a difficult scenario to meet all of the things you need to do. Most of the concrete admixtures have one or maybe two functions. Renolith Nanotech has multiple functions, so we talked about the crack inhibition and reducing shrinkage and improving strength and so on. So all of those things are important for pavements. We've talked a little bit about the product itself. Interesting thing is, because we're not limited by the cement content anymore, it means we can really widen the scope of materials that are suitable for pavements, and it has been used in some really poor materials and quite effective. The first major project in Australia, at least, was the Sydney 2000 Olympics, where it was used at multiple venues, and around the world more than 70 million square metres now have been done. The original product disappeared from Australia for a while, but it's come back now with a second generation formula, which we're calling Renolith 2.0. It's essentially the same as the original, just a double concentrate, so you don't need as much in the mix. So in terms of what's in it, it's a combination of latex, so that's the polymer component. That's well established as an admixture base. The nanocellulose is, I guess, the fibrous part of it, which is something that helps with the tensile strength and holds everything together. And the nanoparticles, we use nanosilica. There's various nanoparticles you can use. Nanosilica is most commonly used in this type of nanotech, and then that has several improving properties around the nucleation of calcium silicate hydrates and improved pozzolanic reactions. Nanotech itself is nothing too scary. It's just about scale. So a nanometer is a billionth of a meter. So nanotech, we're really talking about something of the scale, maybe 10 to 100 nanometers, and that's all it is. Why it's important is because the properties of matter change quite significantly when they're ultra small. There's a lot more surface area to volume. That ratio is quite different. So for pavements and for cemented materials, the things we're most interested in are the strength and crack resistance. In concrete and stabilisation, current guidance is very much focused on materials on the right hand side of this chart, broadly macroparticles. The engineering in that space is mature, microparticles have their place, but where it gets really interesting is in the nano domain. And one of the reasons that nanomaterials are so effective is because they have such a high surface area to mass ratio, so surface interactions are multiplied. And as nanotechnology matures, I expect this will be a very exciting space for pavement engineering over the coming decades. In case you think I'm just making it all up around nanotech, there are literally hundreds of papers out there. Here's just one which talks only about nanosilica and only concrete pavements, and there's hundreds of references just around that. Clearly there's interest amongst researchers. There's a lot of evidence to note that these nanomaterials can improve the performance of the mixes. What's interesting though is that the dispersion and agglomeration of nanotech is quite a challenge, particularly in a pavement scenario. In concrete, you've got a few more options. Perhaps mechanical dispersion would work, but in a typical in situ stabilisation method, such as we're talking about here, it's really quite tricky, and that's where Renolith shines, is because it uses this covalent chemical modification process and allows a very easy method for dispersing the nanomaterials throughout the mix. What happens when we combine nanomaterials with binder, aggregate and water? Basically, in the cement hydration reaction, nanomaterials provide the structure for the formation of additional hydration products, which fill the voids and improve the binding process. In the SEM images on the left, we showed the cured material with cement only. On the right, we see the impact that Renolith or nanotech has on the microstructure. The cement hydration products are more numerous and more formed. Gaps between soil grains are filled, reducing permeability and providing fewer vectors for deleterious substances such as sulfates or chlorides. And the composite has improved mechanical properties such as compressive strength, tensile strength and modulus, and susceptibility to cracking can be greatly reduced. Around Renolith specifically, there's been dozens of studies over the years by various universities and laboratories covering various soils, binders, dosages, applications. That's page 1, page 2 here. These days we're mostly focusing our research efforts with RMIT University. There'll be quite a few papers coming out in late 2025 and in 2026, and hopefully we'll see some other universities pick this up as well. Looking at one of the early studies that was done, this report by Dow, it's pretty straightforward. It's just the lab test results for sand, soil, cement mixes with and without Renolith. The main thing to take notice of here is the improvement in flexural strength and elastic modulus. I mean, it varies by material, but clearly quite an improvement. And as we'll see on the next slide, that has quite a big impact on the fatigue performance. So if we plug in a very complicated slide, my apologies. Let's say we can get a 30% gain in elastic modulus and flexural strength, which is certainly achievable given the test results we saw on the previous slide. If you plug those numbers into the Ostrode's fatigue equation for where that holds for the material, we get a huge gain in the fatigue life. So it's due to this 12th power in the numbers there in the equation. So without changing the thickness of our layer or anything else, you get a orders of magnitude improvement in the life of that pavement. To summarise those benefits, so everybody wins. We have a fast, low-cost construction method which is inherent to in-situ cementitious stabilisation. We're reducing risk, particularly around cracking. We're not experiencing the typical damage modes you'd see in flexible pavements. So I'm talking ruts and potholes and the like. We get a very long life, specifically traffic capacity. We have a highly resilient pavement. We're basically impermeable and not worried about water at all. And that all means very low emissions and ultimately sustainable, both through the construction phase and in use, because we're not repairing and rehabilitating as often. Tying that together, it's about sustainability. We don't have all of the damage modes. We can use any material. We get a very low carbon footprint. We can have a very durable pavement and its broad application. We'll just look at a few case studies. There are more on our website if you want to have a look. This is the list of case studies that are available on our website. We'll look at a few of these. There's all sorts of applications, so paths, roads, highways, freeways have been done. Usually it's the base layer that's been rehabilitated or formed, but sometimes subgrade as well. All types of materials have been used. In most cases it's been Portland cement as the binder, but there's no technical reason why we can't use low carbon binders, and they're certainly more commonly used in Australia now anyway. The amount of binder we put in does vary depending on the material and what we're trying to achieve, just how heavily bound material we want. But there's common benefits across all of these projects that we've seen. So the construction is inevitably been lower cost than the alternates. It's always been faster, and this is all just because of the method, so with cementitious stabilisation. And inevitably there's no cracking achieved, and very high performing pavements have been seen with no in-service defects. There's a link on our website to a letter from the Sydney Olympic Coordination Authority, which we've got just an excerpt from here. They use the product at 8 different venues in heavy in-situ clay with cement, and it was really successful in that scenario. So costs were much less than the alternates, and the big thing of course was time, because they were in a rush to get ready for the Olympics. And they confirmed that it was suitable as a long-term solution, and hence the interest by New South Wales government at the time. The Brenner Autobahn is the busiest truck route between Austria and Italy through the Alps, and they had some pretty severe failures in that pavement, and they needed to rehabilitate it, which they did with Renolith and cement. A little bit of supplementation of gravel, but mostly it was the in situ material that they stabilised. Quite a heavily bound material, so 25 kilos of cement and 30 centimetres deep. And again, very fast, low cost method, not much material use, it was mostly recycled. And in service, that pavement's taken over 30 million trucks already and 150 million cars, and no repairs yet. In Russia, this is the Kola motorway, which extends from St. Petersburg to Murmansk up in the Arctic Circle. So that's about 1,400 kilometres of highway. Quite a big project. They were struggling to find a suitable quarry material in the region, so they just used local sands, strengthened by cement and Renolith. They used a pug mill cold mix in this case, and they yielded some real advantages compared to the alternates. And again, still in good condition despite the pretty extreme conditions that they experienced. In the Australian context, we have pretty mature specifications around cementitious stabilisation, whether it's in situ or plant mixed. Most cases would use in situ, but yeah, every state's got a suitable spec. They all have their pros and cons, but they can all be tailored to align to what we recommend. Again, any type of binder, cementitious binder is fine. If you look in the Austrades guide, there's all sorts of options. Really, it comes down to a local decision. GP or GB cement, triple blends, slagline blends, whatever is most suited to the situation. I mean, there's certainly a push towards using slower setting binders because of their sustainability advantages, amongst other things. But really, there's no shortage of options out there. In Australia, we're limited to the number of binders we might use, but there's all sorts of materials out there that behave a bit like cement in the right combinations. Thousands and thousands of papers on this stuff. So really, it comes down to the context specific. Wherever you are, whatever binders you can get that are going to do the job is fine. And Renolith is just an enhancement to that. Let's tie that together for what it means for sustainability and the circular economy. If we look through a lens of greenhouse gas emissions, so normally a lot of projects would just look at the scope 1 and maybe 2 emissions in construction. There's actually benefits here across all phases, so construction, in use and disposal, and scope 1, 2 and 3 emissions. So we've talked a lot about the use of recycled materials and so on. That's all great. The key, though, I guess, is that if you get the increased life and you don't have the maintenance and the rehabilitation issues, that really reduces your whole of life emissions. And there's some minor benefits to be had through just having a better pavement. If it's stiffer and it's not as rough, then you're using your cars are actually, or your trucks are using less fuel, and tyres aren't wearing as much. So lots of benefits when you tie it all together at that level. It is actually possible to get to net zero, at least in the road construction piece, and it's really following these 3 simple principles. We stabilise, we enhance, and we optimise. We've talked about stabilising. In situ stabilisation is already very well known to have a lower carbon footprint than other methods, particularly if we're using a lower carbon binder. As we've talked about, we had Renolith Nanotech, we get enhanced material properties, and the Renolith itself adds almost nothing to the carbon footprint, so we're getting it for free in terms of overall carbon footprint. So that's if you just take the existing design and add the Renolith. you'll get a much longer life. But then when you look about the optimization options about using different materials, relaxing some of the long-held constraints around how we do business, it really does allow us to drive to net zero. It's not just Australia, this is a global opportunity, and Australia could lead the world in this. If we look at the footprint of road construction across the world, it's massive. And it's growing. There's millions of, millions of kilometres of roads already, and that's going to increase by 60% from when this study was done, 2010 to 2050, plus all the parking spaces that go with it. And of course, it's not just the construction. There's the maintenance, and the refurbishment. They don't last forever, and some jurisdictions the roads last longer than others. Lots of opportunity to do business better by using recycled materials, lower carbon binders, improve our resilience and life, reduce our material consumption, reduce our emissions, reduce construction costs, reduce whole of life costs. Yeah, the opportunity to do things better on this planet is huge and quite doable. So if we take the current path we're on, we've got a growing network, and we're still perpetuating unsustainable construction methods which need frequent repair and construction. A much better path would be sustainable, resilient roads via recycling the in situ material and enhance that by nanotech. Hopefully I have piqued your interest. If so, please reach out to us. We're really keen to take on some challenging projects to showcase the sustainability and resilience benefits of pavement nanoengineering. And there's plenty of state and federal funding for such projects at the moment. Thank you for watching, and we hope to hear from you.